you need to unmute yourself. All right, for the fourth talk, we're going to talk about what's in a caption, and we'll hear it from Andrea Mascaretti.
Thank you. Okay, good. So yes. So what's in a caption? Finding semantics with the information imbalance. So the work we have done starts from a very simple question, which is why do large language models work so well? The reason is simple. Large language models, after all, are trained just to predict the next token, but if you want to abstract a bit, the model is simply trained to predict the next word. And from this very simple training function, you get a plethora of emerging properties like text completion and very good zero-shot learning in translation and other tasks, and few-shot learning. You can correct words and do a lot of things. So the question is, why do they work so well? One of the hypotheses is that transformers are somehow capable to learn the meaning of the thing they process. And so the idea, if you want to visualize it, is there is some space Z, which we do not observe, which is a space of meanings. And then from those meanings, you have that they are mapped towards images or text, which is what we get in real life. And those text and images are mapped to vectors, okay? So for instance, here we have an example with video, audio, and text. They are processed, they become numbers. Those numbers are called tokens. And it's basically what happens. And so the question is, if they are really able to learn the semantics of things, first, we hypothesize that semantic layers should be predictive across languages if they do capture universal meanings. Second, that maybe semantics is captured in some specialized layers. So we imagine that there are early layers that do syntax and deeper layers that do semantics. And third, if size, as it appears, drives the performance of these models, we would expect the larger models should show stronger semantic alignment. Now, the big challenge is how do we measure semantic similarity across different models and across languages? And the proposal we have is to use the criterion, which is called the information imbalance, which is a rank-based metric that does two things mainly. First, it handles different activation scales across different models. And second is asymmetrics, because we want to know if model A captures semantic better than model B and vice versa. So what's information imbalance? It's a very easy metric. And basically, the question it tries to reply is this. Let's say 2 points are neighbors in English, so 2 very similar sentences. The question is, are they also neighbors in Spanish? How do we do this? First, we take the first neighbors of I, which is a sentence in space A, and then we go to space B. Obviously, they are paired. We have paired translations. And we go and check, OK, this sentence, which is the first neighbor in English, is it the first neighbor in Spanish? We count. Maybe it's the third neighbor. And then we average. So we have a scale which conveys a measure of the average rank of A's neighbors in B. Okay? So it's basically a conditional ranking measure. So how do we understand this measure? Well, basically, if they are equivalent, A and B carry identical information, then both indicators will have 0 as a value. If B is less informative than A and A is more informative than B, then we have the information imbalance going from A to B is 0 and vice versa is 1. And if they're independent, both values are high. So the key insight here is that if there is low imbalance, it means they share semantic content across language or modalities. Okay? So let's go to the first experiment. So the dataset is Opus book. So we took novels like Pride and Prejudice, Anna Karenina, and we took sentences from it. We took 2,000 sentences of 40 to 50 tokens. And then we have 2 models to test this hypothesis. The first model is DeepSeek v3, which is a big model with billions of parameters. And just to give you an idea of the dimension of the object, each token has a dimension 248, so each token is a vector, and then we concatenate 50 of them. So we have an object which is of dimension order of big O, 10 to the power of 5. And then we have a smaller object, which is a llama model, so 8 billion parameters. And here, the representation is somewhat smaller, not that smaller, but I think this conveys a measure of how hard it is to compute the distance between these objects. And then the last thing we do, we want to study the correlation across tokens because we want to test the hypothesis. Thus, semantic alignment emerges gradually from syntax, so to early tokens, to meaning, content, words. Okay? So I have results. So that's the first result. And here we have two important examples. So on the left, you see we have English to Spanish pairs in different networks. In blue, we see DeepSeek, and in green, we see Llama model. And you can see that the hypothesis of specialized layers kind of is confirmed with the data because we have the region in the middle of DeepSeek, for instance, which is a bit of a plateau. And what does it mean? It means that the sentences in English, the neighboring structure in English is preserved in Spanish. So I'm able from English to predict Spanish neighboring structures. And you can see that at the beginning, I don't have that. And this is because we think that here the layer, the network is specialized in syntax, yes, and so it's language specific. And also at the end, because when you do an X token prediction, obviously it does matter if you're speaking English, Spanish, or any other language. And you can see that the same thing happens qualitatively with Llama, although the plateau is less pronounced and it happens for less time, let's say for less layers. And the reason is that the size of the model is smaller. And so this is what explains it. Then we tried this with different pairing of languages, so English and Spanish, English and Italian. And we see two different phenomena. First, qualitatively, I get the same. And that's interesting. So it does mean that there is actually a specialized semantic area in the network. But second, the rate of this familiarity is different depending on the pairs of languages I pick. So for instance, English does show a lower value, which means a better alignment. This is because probably neural networks are biased, and the vast majority of the samples they read is in English. And you can see that this regardless of the language, so like Spanish and Italian, they're both Neo-Latin language, so a priori I would expect them to be converging, but then in the end I see that English actually is what drives, I think, the predictivity. And that's interesting, and sometimes people assume that English is this universal language of thought that machines use. Then there is another experiment, and here we try to study the correlation across tokens. So I fix a layer, and I look how predictive I am of a token, going from the last going backwards to the next to last, and so on. And you can see that the behavior of the correlation function depends on the layer. So the first layer has like no correlations from the last token. It's very hard to predict what happens before me. But as I go deeper and I get more semantical, the correlation becomes more pronounced to the point that it's like it shows me that the meaning of the sentence is capturing the entire sequence. And then it goes back a bit. So when it goes back to specializing to the language-specific application. And this happens in Llama and DeepSeek, so regardless of the model. But the phenomenon is way more pronounced when the model is bigger. And it suggests that, yes, size does drive model performance. Then we tried with a different idea. So we thought, OK, let's pair images and captions. So they share the same semantic meaning. But they are encoded in different manners. Okay? So a caption is text, and an image is obviously an image. So we took these images from Flickr, 5,000 samples. And then we took two different networks. The first is Dino, which is a feature extractor. So what it does is try to compress images to get and learn the salient features. And here we have, again, a big object. And then we tried with Image GPT, which is basically a GPT encoder applied to images. So you basically take an image, you unroll it, and then you do next token prediction on it. And for caption, we still use DeepSeek. Okay? And images and caption are processed independently. The network are not fine-tuned. They're just out-of-the-box foundational models. So they are unaware of text or images respectively. That's an example. So we have two people cooking pasta. And we have these human-generated captions. So it's 5 captions, and that's what we use as a description. And the results are here. And so what happens is interesting. First, we see that, again, we find that the semantic regions of the network do inform how predictive they are, regardless of the medium in which the data are encoded. So for Dino, the semantic layers are at the end because the network is trained to output semantic features, and it's in blue. And you can see that Dino is like state-of-the-art networks, and you can kind of see this because the image, which is the dashed line, is more informative of the text. And you see there is a bit of an asymmetry. Whereas with ImageGPT, which is a GPT-like encoder, I have, again, that the semantic region is in the middle, and that's where I have the sort of valley. And you can also see that in this case, DeepSeek does predict better the content, the semantical content, than the image. So the takeaways are, first, that there is clearly an emergent complexity phenomenon in which these transformers, even though they're trained on very simple tasks and on different data, they are kind of converging to this universal semantic representation, which happens regardless of the language of encoding and of the modality of encoding. We see that this is because there is a specialized layers which basically deal with semantics, and the larger the model, the stronger the alignment. So the methodological contribution here is that we try to formalize and quantify these intuitions which are out there, but trying to keep many tokens and many high-dimensional objects. And this helps because it allows to understand which layers are semantic, which layers are syntactic. And maybe for the future, although this is like practical-ish applications, it will be useful for model compression, maybe transfer learning. So this work has been submitted to a conference. There is the preprint available online already. And that's the QR code if you want to read it. And thank you.
Thank you. We have time for 1 or 2 questions.
Really, really interesting work. I mean, like for example, the studies from Anthropic, they kind of like they point into the direction of that representations might be like really learned across several layers. Mm-hmm. Is there a way to maybe take that into account as well?
You mean they're learned across layers in that there is a region which is specialized?
Yeah, maybe something like this. I mean, if I get this correctly, you're investigating like how much, like what's the structure in each representation, but maybe like you might need to take into account like 2 or 3 layers that come after another to really get like the rich picture.
To rich layers? I don't understand the question. Sorry.
Okay. Like you are comparing what's like the richness of representations.
Yes.
In 2 different models. So
yes.
I compare DeepSeek GPT layer 27.
I know, we do all couples of layers.
Yeah, all couples of layers, but
yes.
Like, so my point is more like maybe you need like the summary of 3 layers to really identify like how something is encoded. In order to like really get a score for the richness of the encoding. Is there a way like to maybe incorporate that?
I mean, yeah, I think so, but the summary, how would you, the summary like the average token, you would suggest something like that? Because we're taking all of the tokens mainly now, so the quantification happens by taking all the tokens for each pairs and then computing this score which tells you how the neighboring structure is preserved or not. So I'm not sure what you mean when you say to summarize.
Okay, I would say let's. I just approach you after the talk, and then we can maybe discuss that.
Yes. Okay. Thank you.
That sounds good. Any other questions, Andrea? Okay, I don't see any immediate ones. So yeah, you guys discuss over lunch, and we thank Andrea again.
Thank you.